All right, and example 2 is ready to go. So we have a vector field given as above, and we have a series of questions that we want to answer together. So let's go through them one by one. So for this vector field, can we say it's conservative? And so there's different ways we can think about this. We could try to find f. So question, does there exist an f such that the gradient of f is equal to our vector field? Well, that's one way to go about it. And then the other way we could think about it is we could try and use those ideas of path independence and derivative matrix if we have so those criteria is met of open, connected, or simply connected. Okay. So first of all, this route's going to fail. You can try to find a scalar function until you're blue in the face. It's not going to work. Okay. So this is sad panda. Okay. Then you could also try the other route of talking about open, and it actually, yeah, and this does end up being okay for open. But then if you look at connected, this is where we start to get into trouble. Okay, and in particular, it's not simply connected. Okay, so this one fails. So and you could also look at DF, and this ends up being symmetric. Okay, but because of that lack of a simply connected space in this vector field, we're out of options. And also to note why it's not simply connected is if you look at x squared plus y squared, that you can't have 0 in the denominator, so that excludes the origin, so there's a hole at the origin. So that's kind of sad. Okay, so is f conservative? Kind of unknown at this point. Using our standard approach, we can't say that it is, but we can't say it isn't. So we could also argue, well, so since it is, we could try to use the contrapositive, and maybe that will have some use for us. So another way to think about it. Okay, moving on though to other parts. So here's curve C shown here. It's a unit, well, a circle. Going counterclockwise, removed the origin. And so if we talk about the circulation does not equal 0, why does that not contradict any of our theorems? Okay, so if we think about this for just a moment. So for our theorems, we need that so this, if the circulation is not 0, remember that was the same as it being path independent, it being conservative, right? Well, in each of those suppositions, we kind of said to be safe, we went with a stronger condition of simply connected. So it's not simply connected. Okay, so without meeting that criterion, we can't apply any of our conclusions there. Okay, so given that the circulation is not 0 doesn't necessarily mean that f is not conservative. Okay, now for the last question, why don't we actually be able to do something? Okay, so we're given, so we want to find the circulation where D is the curve pictured below. Okay, so here's what we're going to do. We need to find a space that is open and simply connected to be able to say something. Okay, well, what if I start by saying, okay, I'm going to restrict domain to x is less than 0. Okay, so it's everything to the left of the y-axis. Okay, well, if I do that, then I don't, with my vector field and everything, then I don't have to worry about it. This is going to be open. Domain is open. Okay, and in fact, it is simply connected. Okay, so then the other thing is, in this space, F is C1. Oops, C1. Okay, and then we can then say we already said earlier that DF is symmetric. You can compute it, and I just chose to omit it. Is symmetric. Okay, and then therefore, since the DF is symmetric, it's path independent, it's conservative, and ultimately we have that the circulation of the vector line, circulation on D of F dot ds is 0. Okay, so that's an easy way of computing the circulation, but the idea in this example is to really futz with those assumptions. So in this case, because of kind of how F was defined as having that hole at 0, we were in trouble. We didn't have a simply connected domain, and in C we didn't have a simply connected domain, and then if we were to look at the vector field, we ran into troubles with the denominator and the origin not being included, so that's where we kind of ran into troubles. But finally in D here, we were able to get rid of that by restricting the domain to something where we don't even need to consider the origin. That was where this part came into play. And then once I had a better domain, and that also addressed the concerns in the vector field, then I started to run through my conditions. Is it open? Yes. Is it simply connected? Yes. Is the vector field C1? Yes. And then finally I had to figure out which of the if and only if equivalencies, I guess, I was going to attack, and given that I had the vector field function, it was easiest just to compute the derivative matrix corresponding to it, and I would have found, I didn't do it explicitly in this video, but it would have been symmetric, and then therefore the circulation was 0. Okay, because that was, again, one of those if and only if ideas. Okay, so that wraps up this example. We have one more example to go, and then we'll be done with videos for this week.